Good morning, everyone. Welcome to the class of CE331, Environmental Engineering 1. So, we are discussing water quality and treatment, and under the topic, we are discussing we discussed chlorination last day and breakpoint chlorination, right? So, we discussed this figure step by step in detail, and then we discussed up to this, right? I believe, right? Okay. So today we will start from water softening. So what is water softening? Soft is the opposite of hard, right? So what is hard water? Hmm? What is hard water? Say it again. Say it again. I cannot hear you clearly. I cannot hear you. Can you increase your? Uh, I don't know exactly what's the problem. Still, I cannot hear you. Anyway, so hard water. Hard water means hard to wash, right? Hard to wash. Why? Because it has um, divalent cations like calcium, magnesium, and these divalent cations react with soap, and therefore it's difficult to use hard water to wash our clothes, right? So that's the problem actually. Now, to remove the hardness, to remove the hardness, removing hardness is actually softening. That's called softening. Here, so water softening. Let's see what's the definition here. Hardness consists principally of calcium and magnesium salts. These, while not undesirable for a health standpoint, may take the water less suitable for some non-potable use. That means non-drinking purpose. What is non-drinking purpose? Like as I told you, washing and maybe industrial processes. Okay. Now, benefits of softening to domestic water users include reduction in soap use. So, by using water softening, you can reduce the amount of soap need to be used, and longer life for water heaters, and less incrustation in pipe. Incrustation in means the deposition of material in the pipe. Okay. Now, if water, that's okay, and then now the thing is the two basic methods for removal of hardness are chemical precipitation and ion exchange process. So there are two methods actually to remove hardness. One is chemical precipitation process and another is ion exchange. Now let's see the theory of softening. You have to understand this very clearly. This calcium can be of many forms, like calcium carbonate. Guys, can you see?
जी सर.
This calcium
Yes, sir.
ion, this calcium can be in different forms in water. Okay, what are the forms? Calcium carbonate, calcium bicarbonate, calcium chloride, calcium sulfate, calcium hydroxide. So here you can have calcium carbonate, then calcium bicarbonate, okay, then calcium chloride, calcium sulfate, many forms and others. Among them, all of them, what is the least soluble? Least soluble means it is not dissolved in water. Which form is the least soluble? Least means, as I told you, that least soluble. That means which does not dissolve easily. Solid. What is the form? This is the form. That means they are in dissolved form. Calcium bicarbonate, calcium ion, and bicarbonate ion. Similarly here, sorry, yeah, it's two, right? So yeah. Now calcium chloride, calcium ion, and chloride ion. They are dissolved form, but these are basically aqueous, right? These are basically aqueous. Now, what about this calcium carbonate? This is not a dissolved form. This is basically solid form. And whenever you convert calcium bicarbonate or calcium chloride to this form, then it will precipitate solid. It will precipitate. Is it clear? Similarly, similarly, in case of magnesium, there can be of different forms like magnesium hydroxide, magnesium bicarbonate, magnesium chloride, okay, and others. Now among them, which one is the least soluble? Here there will be two, okay. Yeah, there will be two. I mean, calcium bicarbonate, there should be two here, and magnesium bicarbonate should be two here. Now among them, which one is the least soluble form? This one. That means this precipitates in like solid. That means if you have this form of magnesium in your water, that is basically dissolved form. That is basically dissolved form. Now, in any way, if you can convert this magnesium bicarbonate to magnesium hydroxide, then it will be dissolved. Sorry, it will be precipitated. That means when it gets precipitated here, you can easily remove them, right? Similarly, if magnesium chloride can be transferred to this form, magnesium hydroxide, then it will be precipitated and you can separate them easily. That means this is basically you are removing magnesium from water, you are removing calcium from water. That means you are removing hardness from water. So your objective, remember, your objective is to convert other forms to calcium carbonate and convert other forms of magnesium to magnesium hydroxide. Then they will be precipitated and subsequently be removed from water. Clear? Guys, is it clear?
Yes.
Okay. Now, how we can do this, right? That's the question. The objective of chemical softening, this chemical precipitation process, is to convert all calcium hardness to calcium carbonate. To calcium carbonate and magnesium hardness to magnesium hydroxide. Magnesium hydroxide. Now, how we can do this? That's the question. Let's see. The addition of chemicals like carbonate and hydroxide elevates the pH. The addition of carbonate and hydroxide elevates the pH and increase the pH. Okay, boost the pH, which shifts the equilibrium of the carbonate acid system in favor of the carbonate ion, and it changes the alkalinity from bicarbonate to carbonate form. As you know that with increasing pH, the alkalinity changes from bicarbonate to carbonate, and this increases the concentration of carbonate ion and shifts the equilibrium to the right. That means calcium carbonate, if you increase the pH in this equation I'm talking about, then the equilibrium, then carbonate ion will increase and the equilibrium point will shift to the right, and you will get more and more of calcium carbonate. Similarly, in this equation, if we increase uh, the hydroxide ion, then the equilibrium of this equation will be shifted to right, and you will get more and more of magnesium hydroxide, and these are solid, so they will precipitate. They will precipitate. Is it clear? So in order to precipitate calcium carbonate, the pH must be raised above 8.3. In order to precipitate calcium carbonate, that means in order to precipitate this calcium carbonate, your pH must be greater than or equal 8.3. Okay, so greater than 8.3. Optimum is 9 to 9.5. Okay, to convert bicarbonate alkalinity to carbonate alkalinity. If there is not sufficient natural occurring bicarbonate alkalinity for the calcium carbonate to precipitate, we must add carbonate source. We'll see how. That's one thing for calcium. For magnesium, the pH must be raised above 10.6 to convert carbonate alkalinity to hydroxide alkalinity. That means to get this, your pH must be raised above 10.6. So this is even more grueling or arduous. Okay. Now let's see the equation. There can be different operating conditions. Number A, when your alkalinity is greater than hardness. Alkalinity is basically what? Acid neutralization capacity, right? And hardness is the presence of divalent cations, right? So when your alkalinity is greater than hardness, when your alkalinity is greater than hardness, what does that mean? That means that you have sufficient alkalinity in water. You have sufficient alkalinity in water. And remember, what is basically alkalinity? The acid neutralization power. And where does it come from? Basically, it comes from a bicarbonate ion, carbonate ion, and what else, guys? Huh? What else? Hydroxide ion, right? Now, if you have alkalinity greater than hardness, that means your alkalinity is higher. That means you have sufficient amount of bicarbonate and carbonate. You have sufficient amount of bicarbonate and carbonate. Now, what's your objective? Remember, your objective is to get this. Your objective is to get this. You already have calcium in your water. Now, you also have a bicarbonate and carbonate. So use them to get what? Calcium carbonate. For example, this carbonate. So calcium carbonate. And then your job is done. It will precipitate like this. So calcium will be removed. And for this reaction to happen, your pH has to be, remember, your pH has to be greater than or equal 8.3. So pH has to be greater than or equal 8.3. How would you achieve it? How would you achieve it? That's the question. Okay. So that's basically you can achieve it by adding some basic material like calcium hydroxide, like lime, calcium oxide. Basically, in water, it reacts with water to form calcium hydroxide, and this actually increase the pH of water. This increase the pH of water. So what happens that the thing is, if I summarize this, then you have calcium ion in your water. You also have alkalinity in water. That means the condition is alkalinity is higher than hardness. So you have bicarbonate ion in your water. You have carbonate ion maybe in your water. Now, what's your objective? Your objective is to get this. What you are doing, what you have to do, that means you have calcium ion, you have bicarbonate ion. That means you have calcium bicarbonate. In your water, you have calcium bicarbonate, right? Now you add this calcium oxide plus H2O. So what you have done, you have added this. This is the lime basically. have added lime here. Okay, and when you have added this lime, it will basically increase the pH. Okay, increase the pH. And when it's greater than 8.3, it increases the pH to 8.3. Then this calcium ion will react with calcium oxide, that lime, to give you calcium carbonate. Okay, this is a mistake. It will be this. Correct this. Okay, calcium bicarbonate. So calcium bicarbonate, you add calcium oxide, it will give you calcium carbonate plus water. Instead of calcium oxide, lime, you can also use sodium hydroxide. This is also a base that will also increase the pH to, um, we are calling it 8.3. They are also taking it at optimum level, so 9 to 9.5, right? Let's call it 9.4 or something like that. So it's even better. So 9.4, at least 8.3, you have to increase it. So 9.4. How you have increased it? By adding calcium oxide. And then you got this. Or you can add sodium hydroxide. That will also raise your pH to this. And then this will be converted to calcium carbonate. And this is, whenever you will get this, it will precipitate. It will precipitate. Is it clear? Guys, is it clear?
Yes, sir.
Now, condition B. It may happen that your water alkalinity is low. That means your alkalinity is less than hardness. Previously, you had sufficient alkalinity. That means you had, uh, that means you had bicarbonate ion in your water, sufficient amount. Previously, you had this. Now you don't have this. Now you do not have this. That means the hardness you have, that is not basically calcium bicarbonate. That is not in this form. That is not in this. Previously you had calcium in this form. Now you don't have this in this form. Maybe in this form, in this form, or in this form. What you have to do now? Like calcium chloride, calcium sulfate, or calcium nitrate. Okay, this means it is calcium chloride, or calcium sulfate, or calcium nitrate. So now you have calcium chloride, or calcium sulfate, or calcium nitrate. Okay, now what did you do? You'll have to, previously you had calcium bicarbonate, here you had calcium bicarbonate. Because why? Because you have bicarbonate, because your alkalinity was higher. Alkalinity was higher. The alkalinity was higher than hardness. But here alkalinity is less than hardness. That means you do not have this bicarbonate ion here. For example, calcium chloride. Now remember, previously what happened? There were calcium bicarbonate. You added lime to increase the pH, and then this hydrogen was separated and it became calcium carbonate. So carbonate was already there. Here carbonate was already there. Where? In the bicarbonate, calcium bicarbonate. But here you do not have you do not have carbonate in your solution. Can you form calcium carbonate now in this way by adding calcium oxide? Where did this carbonate come from? Are you following me? You do not have this carbonate now. Like, unlike the previous case, you do not have the carbonate now. You have carbonate here, you don't have carbonate. But you had carbonate here. Is it clear, guys?
Yes,
Yes,
sir.
sir.
Yeah.
Therefore, you have to add carbonate now. You have to add carbonate. Sodium carbonate. Sodium carbonate. This is called soda ash. Sodium carbonate. This is called soda ash. What is soda ash? Sodium carbonate. Now you add sodium carbonate. That will also raise the pH. That will also raise the pH. And then this calcium and carbonate will react together to give you calcium carbonate and sodium chloride. This sodium and chlorine, sodium chloride. Clear? And it will precipitate. This is it's a least soluble form, so it will precipitate. Calcium carbonate and sodium chloride. If it is sodium calcium sulfate, then it will be if it's calcium sulfate, then it will be sodium sulfate. If it is calcium nitrate, then it will be sodium nitrate. So this has been shown to show the alternate forms like calcium sulfate or calcium chloride or calcium nitrate. You can use any one, no problem. You can use calcium sulfate, then you'll get sodium sulfate here. If you use calcium chloride, you will use sodium chloride here. If you use calcium nitrate here, then you will get sodium nitrate here. That's not an issue. So what the uh, take home message here is that when your alkalinity was higher, you already had bicarbonate here, so you do not need to carbonate. You just add lime and then calcium carbonate. But when your alkalinity is low, then you don't have bicarbonate in your water. Okay, so you have to add carbonate, sodium in the form of soda ash like sodium carbonate, and then you will get calcium carbonate. Is it clear?
Yes, sir.
So tell me if you have any questions so far. This is important, okay? You need to know these things. It's very simple, again, very simple. Your objective is to get calcium carbonate. Your objective is to get calcium carbonate. Now, there may be different issues. Number condition one is alkalinity is higher than hardness. That means alkalinity is higher means you have bicarbonate and carbonate. You have bicarbonate, that means calcium is in calcium bicarbonate form. But in condition B, your alkalinity is less than hardness. Less than hardness. Therefore, you do not have bicarbonate. Alkalinity is low, so you don't have bicarbonate. So in that case, may have calcium chloride. Now, how you can get from this to this, from this to this? You have to increase your pH at least 8.3, or optimum is 9.4. How you can do this? You have to add something basic, right? And what base you will use? You may use lime, that's calcium oxide, lime, or you may use sodium carbonate, right? So that's also basic, sodium carbonate. Which one you use? Look at here. You need to have calcium carbonate. You already have carbonate here, so you don't need this carbonate. So you use this calcium oxide, okay, plus water. it will form calcium carbonate. Clear? It will form calcium carbonate and plus H2. Now in this condition in B, you do not have carbonate this portion. You do not have carbonate here. So you add extra carbonate. So sodium carbonate. You add sodium carbonate, and then this is soda ash. This is called soda ash. Soda means sodium. Soda comes from sodium and carbonate. Soda ash. So from here you will get this carbon, this calcium here, and this carbonate will react to give you calcium carbonate, and this sodium and chloride, sodium chloride. Okay, clear?
Yes, sir.
So this is basically calcium carbonate is solid form, so it will precipitate. It is solid form that will precipitate. So yeah, now removal of magnesium hardness, addition of lime or caustic soda. One is, I mean, listen, lime can also be represented like this. When you add lime in water, this lime, if you add lime in water, calcium oxide plus H2O, it gives you calcium hydroxide. Okay, so lime can also be represented like calcium hydroxide. So anyway, so addition of lime, calcium hydroxide or caustic soda, this is caustic soda, to raise pH 10.6. Remember, to get magnesium hydroxide, your pH has to raise above 10.6. For calcium carbonate, it was 8.3, but for magnesium and magnesium hydroxide, this is 10.6. So if your addition of lime of calcium hydroxide or caustic soda to raise the pH 10.6 will precipitate magnesium hydroxide. Now look at here, to precipitate magnesium you need this form, magnesium hydroxide, this form, magnesium hydroxide. So there is no carbonate issues here. There is no carbonate issues here. So there is no need to think which one to use, sodium carbonate or calcium hydroxide. You don't need to think about it. Okay, so you can use lime, maybe calcium hydroxide. Calcium hydroxide is what? Calcium oxide and water. Okay, so this will give you calcium carbonate and magnesium hydroxide. If your pH is raised or elevated above 10.6, it will give you magnesium hydroxide, and this is solid, so it will precipitate. Similarly, you can also achieve this by using sodium hydroxide, which will raise the pH above 10.6, and you will get magnesium hydroxide, sodium carbonate and water. Okay, now if you have both calcium and magnesium hardness in your water and you want to remove both of them together, then what you can do, you can use, you have to use both sodium carbonate uh, and lime to raise the pH above 10.6 for magnesium hydroxide and calcium carbonate to precipitate. So if you, for example, if you have magnesium in chloride form or sulfate form or nitrate form, if you add lime, it will increase the pH to above 10.6 and you will get magnesium hydroxide and it will precipitate. And what you have, and you have added lime, right? Lime is this here, and you have added soda ash. sodium carbonate, this one. So this is this. You have added both. So you have calcium, if you have calcium sulfate, calcium chloride, or calcium nitrate, whatever, if your pH is above 9.4, which is 10.6 here, that you'll get calcium carbonate and sodium chloride and whatever relevant form. And calcium carbonate is least soluble, so it will dissolve in water. That's how you remove magnesium hardness and calcium hardness simultaneously from water. Clear?
Yes, sir.
Okay, so remember one thing, complete removal of hardness cannot be accomplished by chemical precipitation. Okay, if your hardness is 200, like calcium hardness is 200 milligram per liter, if your calcium hardness is 200 milligram per liter, then you can reduce it to maybe 20 or 40 milligram per liter. Okay, but not beyond that, not below that. Basically, like you cannot make it 5 or 10, you can make it 40 around. Okay, and for magnesium it's 10. Okay, recarbonation. What is recarbonation? um, what you have done here, you have converted your calcium ions to calcium carbonate. That means your water is saturated with calcium carbonate now. Okay, calcium carbonate is saturated, so much calcium carbonate. Now, if this is your water treatment plant for Dhaka Wasa maybe, and you if you want to supply after hardness removal, you want to supply it to your home. What happens that this is saturated with water, in water. This um, precipitation of supersaturated solution of calcium carbonate will continue slowly তার মানে কি হবে, whenever you supply it in water, the slow precipitation will also deposit here in the pipeline, and that's the problem because this will clog the pipelines eventually. So what you want to do is you co- some calcium carbonate, you uh, return it back to calcium bicarbonate. So some calcium carbonate here, you return it back to calcium bicarbonate. Otherwise, the supersaturated form will saturated slow saturation and slow precipitation will actually reduce. Sorry, that will actually precipitate in the pipe. That's the problem. How you can do this? You can reverse it by using carbon dioxide. So you have calcium carbonate, using carbon dioxide it will be calcium bicarbonate again, and that's how you minimize the chance of deposition in your pipe. Okay, that's called a recarbonation. Recarbonation, adding carbon dioxide. Aeration. Aeration, the word comes from air. Aeration. Aeration. This is basically adding air. Adding air. Let me use this. So aeration is actually aeration is nothing but adding air. That's it. What you have in your air is oxygen. That's it. We need this adding oxygen. Okay. There are a multitude of benefits of adding oxygen. That means air to water. We'll see this in water treatment. Okay. Aeration is a process used to remove undesirable gases, carbon dioxide, hydrogen sulfide, fluoride, or volatile organic dissolved in water. Volatile organic materials dissolved in water, or to add oxygen to water to convert undesirable substances to a more manageable form. Although carbon dioxide and hydrogen sulfide gases are only slightly soluble at atmospheric conditions, groundwater may contain considerable higher concentration under pressure commonly found in deep aquifer. We already discussed these things. Now what we do here is this theory. Liquid gas contact systems are designed to drive the water gas mixture toward equilibrium as quickly as possible for degasification purposes and to provide supersaturation of oxygen for oxidation purpose. That means what? Liquid gas contact systems are designed to drive the water gas mixture toward equilibrium as quickly as possible for degasification purposes. That means um, if you look here, this is your water. So this is here, this is air, and here this is water. So interface, in this interface between air and water, the gas in air, for example, oxygen, and water, in water also you may have uh, gases dissolved, carbon dioxide dissolved, oxygen dissolved. Are you following me? In water, you can also have carbon dioxide dissolved, oxygen dissolved. Are you following me?
Yes,
Yes,
sir.
sir.
Yes, sir.
Now, if your carbon dioxide concentration is higher here and your carbon dioxide concentration is lower here, then then there will be gas exchange. That means carbon dioxide will flow from higher concentration to lower concentration. It's like diffusion. Is it clear?
Yes, sir.
So carbon dioxide, if carbon dioxide concentration is higher here and lower here, the carbon dioxide will flow, and this can be any gas, gas X, for example, gas X. Okay, so your air also has oxygen. You can, if you continuously pass this air into the water, you pass it through the water, then the oxygen in air will get into the water. So more and more oxygen will be dissolved in water. That's one purpose of aeration. Let me give you an example. You have aquarium in your home, right? and you have fishes, right? And you have fishes. Now you have already saw, you have already seen that you use some bubble in a tube. Maybe there are pores, and you use bubble, right? Did you see the bubbles? Huh?
Yes, sir.
Yes, sir.
Now these aquatic species need oxygen dissolved in water. That is dissolved oxygen in water. Dissolved oxygen in water to survive. Otherwise, they will die. Now, therefore, you add air into this water, and this is basically the bubble. This bubble is basically the air, and you're passing this bubble, that means air, into the water to dissolve more and more oxygen, that means dissolved oxygen in your water, so that your fish can survive. That's the objective. And to survive majority of the species in water, it has to be at least greater than or equal 4 to 5 milligram per liter, approximately milligram per liter. Okay. Otherwise, if it's below 4 or 3, they will die. So that's the reason why you continuously add air in the water to increase the transfer of oxygen from air to water, from air to water, oxygen. And that is basically dissolved from, so we call it dissolved oxygen. Is it clear?
Yes, sir.
Now there are, I already just told you one purpose of this aeration. This is also an aeration, adding air. So adding oxygen into the water, there are many benefits. One is this, and in water treatment, let's see how it helps us in water treatment. Okay. Okay. Before I go there, how it helps us in water treatment, um, let's discuss how you can do this aeration. How we can do this aeration. Now, this aeration can be done or accomplished by either dispersing the water into the air, and by dispersing the air into the water. The example in aquarium like this, we are dispersing the air into the water. We are dispersing the air into the water. Now there may be other examples. One is this. This is aquarium. Dispersing the air into the water. What happens here? By dispersing the water into the air, what happens? For example, uh, you have a pipe, you have a sprinkler here. There are many sprinklers here, many sprinklers. Okay, and you have a tray. Now you are adding water, and these sprinklers are spreading water like shower, rain shower, drop by drop, drop by drop. Okay, and then basically a- air are getting in contact with water, or water is getting in contact with water, and then you're collecting them here. So this is dispersing water into the air. Okay, the objectives of the aeration process are to maximize the area of contact between the water and air, maximize the area of contact between the water and air, have an increase of an interfacial area through forming water droplets. In a glass like this, if you have 100 ml water, tell me that what is the area that is in contact with air? Maybe this one, right? Now, if you take this same amount of water into a plate like this is also 100 ml. Did you see now that more and more water is now in contact with air in comparison to this case? Unlike this case, now more and more water is in contact with air because we have increased the interface between the air water contact. Okay, so you can do this in like increasing the interfacial area, or you can do this what you can use a sprinkler here, sprinkler at the bottom maybe, and then it will spread out. So more and more water are now in contact with water and you collect it. So more and more oxygen from air will go or dissolve in the water because this is droplet, right? When you make droplet, okay, when you make droplet, then this can get oxygen from all around, okay, from all around. Unlike this case, only this portion is in contact. But now, if you make them droplet, billions of droplets, then much higher surface contact will be there between the water and air, right? Right, guys?
Yes, sir.
So that's what the maxima is the area of contact between the water and air. Now, to increase the exposure of time of contact, projecting water very high or dropping the water from it. That means, you know, if you have if you drop the water from a four-story building, then between and you collect it here. So four-story building, the time required for the water to come from there to there is, for example, T1. So what is the contact time between the water and air? T1. And for example, this is 10 seconds. Now, if you do it from a 20-story building instead of four-story building, then time of contact will be much higher, right? Maybe 40 seconds or something like that. So aeration will be higher here. Higher is the contact time, higher is the elevation, higher will be the contact time, higher will be the aeration. So contact time, increasing the contact time, that's also a method. To produce motion of one fluid relative to other so that exchange can be enhanced by maximizing the concentration gradient. What is that? This is a little bit tricky. Look at here. This is a glass of water. Okay. Now, if you consider this water at multiple layers, one layer, two layer, three layer, four layers, five layers, multiple series of layers. Okay. Now, layer number one, layer number two, layer number three, layer number four, and successively others. What happens here is that this layer number one is closest to air. layer number one is closest to the air. That means this is directly in contact with water. So oxygen will come first at this level. So oxygen concentration is higher here at this level. If we draw this, oxygen level is higher here. Now there is a barrier from air to layer 2. There is a barrier of layer 1. So oxygen concentration will be lower in layer number 2. In layer number 3, oxygen will level will be further, will be much below than layer number 2. And layer number 4, oxygen is even further below. So this is the gradient will look like this. Um, so the gradient will look like this, right? So there is a concentration gradient. Why this is happening? Because there is no much mixing between this layer and this layer. Therefore, oxygen oxygen transfer is hindered between the layers. Now, this is stagnant water. Okay, okay. Now, if you do this, you continuously use a stirrer, for example, a spoon, and you continuously mix this water. Then what will happen? This concentration will oxygen will be mixed, right, from this layer, so this layer will come here, this layer will come there, so there will be a continuous vigorous mixing, and thereby this gradient will not be present because now they are well mixed. So oxygen concentration here will be almost similar to there, will be almost similar to there. So this is like this instead of this. So that's how you increase the aeration, by mixing them. Turbulence produce motion of one fluid relative to other so that the exchange can be enhanced by maximizing the concentration gradient. Okay, is it clear?
Yes, sir.
Methods of aeration. So as I told you, spray nozzles can be used, cascade towers, when from an elevated tower, waterfalls, then multiple tray towers. Okay, you can use multiple trays, like here is one tray, here is another tray. The water first will come from there and sprinkle in this layer, and then from there to there. So there may be different methods. Water is lifted and allowed to fall from a lower elevation through a series of perforated plates. So this is basically water in air aeration. But air in water, diffused air aerator, like aquarium, I told you, you are passing air into the water, and mechanical aerator. Propellers are used. In this case, propellers are used. Okay, propellers means like fan, like, okay, propeller, like blade, like plates are rotating. Okay, propellers. So objectives of aeration: primarily increase pH value greater than 7.3 through stripping out carbon dioxide. Now, what happens that when you add oxygen in water, remember, you have oxygen here, you have carbon dioxide also here. Now, when you perform aeration, then more and more oxygen is getting into the water, and it will drive out carbon dioxide. More and more oxygen will get in and drive out carbon dioxide. If carbon dioxide is present in water, what does it give to you? H2CO3. That means acid. So carbon dioxide means carbonic acid. That means acid. So carbon dioxide means pH is less, right? Acid means what? pH less, right? Hmm?
Yes, sir.
Now if you drive out carbon dioxide, then your pH will be higher, right? You're driving out carbon dioxide, so your pH will be higher because acid will be reduced, so pH will be higher, right?
Yes, sir.
Your pH will be higher in this case. So increase pH value above 7.3. But since this is not chemical, I mean direct chemical addition, so you cannot increase your pH much, like 9.4 or 10. Okay, this may be 7.3 for stripping out carbon dioxide. That's primarily. Secondly, oxidize iron to from ferrous to ferric iron through adding oxygen. This is very important. You know, if you have iron in your water, which is a big problem in our country, like our groundwater has in many places in Bangladesh, I mean, a myriad of places in groundwater, you have higher iron concentration. You have to remove them. Now, iron in water that remains in aqueous form, I mean, ferrous form. This is aqueous. Ferrous. Anyhow, if you can oxidize it to ferric, then this is solid form and it gets dissipated. That's how you can remove it. So for the iron removal, for the iron removal, this process of oxidation from ferrous, if you can oxidize it using oxidizing agent to ferric, then you can remove it. Okay, so if you can do the aeration, if you can do the aeration, then you can achieve iron removal. That's why aeration is incredibly important in water treatment. So by using aeration, means oxygen addition, you can convert ferrous to ferric form. This is ferrous and this is ferric form. And when you convert it to ferric form, it will precipitate. Then that means it has been removed. Is it clear, guys?
Yes, sir.
So um this is actually ferrous and this is ferric form. Okay. Ferrous and ferric. This is oxidized. As you can see, oxygen is getting in because we are doing aeration, and therefore carbon dioxide is getting out. Carbon dioxide is getting out. Agitation means giving turbulence in water. Okay. Dissolved iron and manganese are often found in groundwater from wells located in shale, sandstone, alluvial deposits. Manganese is an associated problem with iron in most of the places of Bangladesh. So you need to know this. Most of the places of Bangladesh, this is a problem, big problem. Okay. Now, this reaction I just told you from ferrous to ferric, this reaction for this reaction to happen with sufficient speed, your pH has to be greater than 7.5. If it's less than 7.5, then this reaction is very slow, almost zero, very slow in pH less than 7.5. So for this reaction to happen with aeration, I'm talking about aeration, your pH has to be greater than 7.5. If you want to do it with aeration, your pH has to be greater than 7.5. So reaction rate are strongly pH dependent, and there is a second order relationship. So quite slow at pH less than 6.5. You can call it 6.5, and very rapid at pH greater than 7.5. So less than 6.5, this is almost zero, very slow, and it's very fast if your pH is greater than 7.5. Okay, remember pH is this small p capital H. Always remember small p capital H, pH. Here, this is a since I'm writing with my mouse, so sometimes it's not clear. So I just wanted to tell you separately to make it clear. Alkalinity. Oxidation reaction is incomplete and very slow for low alkaline water. That means if you want to remove your iron by using aeration, by I'm talking about aeration, not chemical addition. By aeration, ferric form, and this is solid, it will precipitate. You have to remember always that your pH must be your pH must be greater than 7.5, and your alkalinity of water must be greater than 130 milligram per liter. We call it even more than that, at least 150 milligram per liter or 200 milligram per liter. Okay, at least greater than 130 milligram per liter. Otherwise, it will be very slow. So for this reaction to happen, if you have to meet this criteria operating condition: pH greater than 7.5 and alkalinity greater than 130 milligram per liter. If you want to do it using aeration, and we prefer this because air is free, right? Do you need money to buy air? Huh?
No, sir.
So still, Alhamdulillah, we don't need to spend money to buy air, but the way we are polluting the world. Who knows? In near future, we may need to we may need to spend money to buy fresh air. There will be air, but that will be polluted all around. So you need money to buy fresh air. Okay. So since this is free now, we don't value it. So we are polluting our environment egregiously, enormously, massive pollution. Okay. Uh, anyway, so that's a different topic. So aeration is sufficiently rapid only if it is catalyzed or accumulated of oxidation products like ferric oxide, manganese oxide, or a porous bed, previously precipitated iron served to catalyze. So we'll see what is this. So for pH, for this reaction, iron removal, your pH has to be greater than 7.3. Alkalinity has to be double greater than, that means much greater than 130 milligram per liter. We call it 150 200 milligram per liter. And absence of organic matter. If your water has organic matter present in it, that will also interfere with this reaction and slow it down. So it's also important that your water doesn't have any organic matter. Okay. Now this is the reaction. Tell me one form of ferric oxide, right? Ferric Fe plus 3 and oxide, right? Are you following me? Ferric oxide,
Yes, sir.
Fe2O3, ferric oxide. Okay. So this is basically ferric form. So this is solid. This is basically the solid form. So when it will precipitate, you will get this form, ferric oxide. And other ferric hydroxide also possible. Ferric hydroxide, that's also possible. FeOH3 because it is ferric. So 3 ferric. So 3 ferric. This is basically solid. It will deposit like this. Now there is an interesting thing here. Um, this this is solid, right? And they will create a flock, ferric oxide or ferric hydroxide flock. They are solid. Interestingly, this flock, ferric oxide or ferric hydroxide, they act as catalyst. They act as catalyst, positive catalyst to increase the rate. So one way you are getting ferric form like ferric oxide and ferric hydroxide after oxidation of ferrous, and these forms which has just formed, these substances which has just formed, they act as a catalyst, positive catalyst for this reaction. So more and more, so this reaction rate will increase. So more and more iron, ferrous, will now be um, converted to ferric form. Okay, is it clear?
Yes, sir.
So that's what they're telling, that aeration is sufficiently rapid if it is catalyzed by accumulation of oxidation products like ferric oxide or manganese oxide, ferric oxide. Okay, sometimes manganese oxide is also formed. We'll see in case of manganese. Okay. Uh, and moreover, these, whatever I told you, that ferric oxide, they have adsorption capacity. These are solid, right? They have adsorption capacity. They can absorb them. They can absorb them. Okay, absorb them. So that's also a way how they can increase the removal of iron from water. So we will discuss this in detail in the next class. Theory of iron removal as well as theory of manganese removal. Okay. Okay. So let's. If you have any questions, you can ask me right now. Any questions? No questions. Okay then. Thank you very much for attending the class, guys. Have a good one and stay safe.